Alrighty. So I'm going to first sort of tell you that we're not going to do equations today. We're going to study geometry with lines. And what we're going to look at is how things happen at infinity and how we can use our understanding of what's going on at infinity to tell us what's going on inside our space. Okay, so we first need to construct some models of this hyperbolic plane. The hyperbolic plane is a -1 curvature plane. Okay, so we have some models to understand what this might look like. And you might be, well, why do we call them models? Well, it's the same way when you look at a map of the geography, it hones in on different aspects. You have a topographical map. You might have a global map that's flat. It's sort of just modeling maybe area, you know, but it distorts some things. So each of these models distorts a little bit of things, some more than others, and we'll just get started with the easiest one to actually draw what lines are. So we need to focus on, since we're not defining equations, I need to tell you what straight lines are and maybe a couple ways to view some angles. Okay, so the first one, so models. So we're going to look at models of the hyperbolic plane. Models. Okay, so the first one is either called the Kleinian model, or we'll take a, as some people call, a neutral name. So it's called the projective disk model. So projective disk model. Okay, so what the projective disk model looks like is a disk. Okay. Okay, so we have a disk. Points inside the disk are the points in our space. Okay? So how do I draw lines? Well, these are great. They're just straight lines like we know and love that connect the edges of a circle. So like chords, for example. Let's draw one over here. Well, we'll draw this one. Okay? Just because it's here. Now, this messes with angles. This is modeling something that does not show us angles correctly. Namely, they're really hard to see. So don't look for angles here. I'll tell you how to look for one particular angle that's important, called right angles, or orthogonality of lines. So say I want, so here's a line L right there. So I have a line L, and I want to know what something is that's perpendicular to this line. Okay, so the way we do this in the projective model is we draw tangent lines so, at the points of intersection of the circle. Oh, that's way off. So we draw our wonderful tangent lines that we've known and loved since calculus. And there'll be an intersection point right here. This point is outside our space. It's beyond infinity. Okay? The circle is infinity. So what we're going to do is we're going to draw lines inside of our disk that, if we had space outside infinity, go through this point. So see, we're not in the space, and then all of a sudden we're in the space. So note, this is L2. It's a line. Right? By definition, it's a line. It's just a chord. And it is perpendicular. So note, L is perpendicular to L2. So this is really weird, you see. There is a line that you can see the angle better. So, namely, that one. So this is also perpendicular to L, right? And that's how we build all perpendicular lines, is we draw these tangent lines, look at the point, and draw lines through those points. And that gets me normal lines. So let's see. That's a right angle. That's a right angle. So it messes with angles. But it's really easy to draw. They're just straight lines. Okay? So we started with the easiest one to draw, but the most distortion of angles. So let's go to the flip side. One that's really hard to draw, but doesn't distort the angles. This is called the conformal disk model. Often Poincaré's name is attached to this model. Okay? So once again, I draw a disk. Okay? So I draw, it's close. And how do we draw lines in this model? So I'm just going to write it up first so that when I draw it, you'll know what I'm trying to do. So lines are open diameters. Okay? And open, this is the hard part, circular arcs perpendicular to the boundary of the circle. Okay. So remember, in both of these models, we think of the boundary of the circle as points at infinity, right? So what we're going to do is we're going to draw open chords. So just a straight line, for example. So open diameters, right? And then we're going to draw. So the way to sort of visualize this is you pick 2 points at infinity, right? Here and here. Okay? Then draw the sort of tangent line locally. I need to shoot out of this orthogonally, right? Because I'm perpendicular to the boundary. So it's going to come in like that. Okay? And likewise down here. Okay? And now we're going to visualize drawing a circle that is this way. So I'm going to stand back and think about coming along. And then I look towards this point and think, draw a circle. And that's a line. Okay? They're hard to draw. Okay? Note we could, here's one more. Just to sort of show you where the picture, we're thinking of these at infinity, right? So I could draw a line that comes out just like the red does from this point at the boundary. And I can draw a line over here that comes out from this orange spot on the boundary. See, once again, I think I'm a circle. Connect them. So we're getting a better view of like how we actually can build these triangles whose vertices are at infinity. Okay? So we're just missing one more. We start up here, right? And we come down here. I'll use another color. So we have a plethora of colors. Okay? So I'll connect this one and this one. There we go. And there we go. There's a triangle for you. Because of the curvature of the space, you can actually do some calculations with integrals and your actual coordinates and see that this triangle will be of area pi. Okay, pi's everywhere. We'll soon have pi's, right? Because we're in math club. Okay. And now the last one that I'm going to show you before we do our activity. So let me make sure. We're going to look at something closer to this model in regards to angles, but closer to ease of drawing. Not necessarily everything's curved. Everything's not exactly curved because you have these diameters, but I want more lines that are easier to draw. And I also want my circles that I'm drawing to be easier to draw too. So let's look at another model which is very important. This is a model that a lot of calculations happen in. It's called the upper half-plane model. So we think of points in C. So here we are. So maybe U2 is going to be complex numbers such that the imaginary piece is positive. Okay. Ah, nice. That's not bad. So this will be the real axis. So now I need to tell you what lines are. Okay, well, what are lines? So lines are open rays orthogonal to the real axis. Okay? And second, open semicircles. So I couldn't get away from the circles, but they're at least now semicircles, and they're orthogonal to the real axis as well. This is nice because a semicircle being orthogonal to the real axis means that the center of the circle is on the real axis, right? So when I start drawing lines, so like we have here, this line and that line, this is the open rays orthogonal to the axis. And then we have half circles. Orthogonal to the boundary. Okay. These are three models, and towards the end of the talk, if we have time, we'll go over the fourth. But the fourth is a lot harder to draw, and I wanted you to actually start doing some geometry in hyperbolic space. So what I want everyone to do is come over here and get some string and line up on this side of this hyperbolic plane. This table, this is the real axis on this side. We're going to be looking at the upper half-plane model. Note how strategically the upper half-plane is located. The boundary, oh, here, distribute some tape. See, we're going to have to draw stuff on the table, so I brought tape. And we need, all right. Yeah, I'll stand at infinity and give you guys string. Because we need to draw circles, right? And string's easy to use to draw circles, so we know where to place the tape, right? Yeah, we need to get everyone on the real axis at infinity. I get to stand at infinity. You guys get to stand at other infinities.
Should we like move down a bit that way? There's more room there.
Okay, we're going to let you guys cut. Do we have more? I should have brought more scissors. Okay. So we need scissors.
I've got some in my office I can bring to you.
Let's see if I can quickly do this. Yeah. There's some pink string. So everyone just needs to get some string. Where's the other roll? We'll get some orange going. All right, so what we're going to do is we're going to practice drawing geodesics or lines through points. Okay, so you can pair up and draw some lines. You might need some help. Someone like doing tape to sort of put little markers along, so you can track where your circles are going. And I'm going to come along and put some points down. So maybe group up in like groups of 2 or 3, and we have tape. So, and I'll go up to the board and show you the activity. Where are those pencils?
Right over here.
Okay. These pencils can be useful to mark on the tape. So we have a point right here. Okay? And then we're going to have another point here. Okay? So go ahead and put 2 pieces of tape down in front of people. And pretty close to the real axis, close to infinity. And mark little stars. And then we're going to think about why I might have given you string to talk about how to draw a line through those 2 points. Think about what lines are in the upper half-plane model. What would be the easiest 2 pieces of tape to put down to draw a geodesic through, or a line? Think of what would be the easiest. Yeah. So you guys got your 2 pieces of tape in front of you, marked points in the hyperbolic plane?
Getting there.
Getting there? Okay. So I'm going to strategically leave up the definition of what lines are. So here you guys are, right? You're here, and you have a point here and a point here in hyperbolic space right in front of you. You are currently, here I'll stand in front of you, you're viewing me at infinity. You guys are all at infinity as well, but I'm labeled infinity, you guys are labeled with real numbers. But we're all at infinity now, okay? I need to think about what it means to draw a line through these 2 points in hyperbolic space. I need to know one thing that has a certain property. I need to know where the center of what is. I need to know the center of this blue circle such that what happens? Okay, the circle will be on the real axis. Yeah, the circle that you make has to intersect the 2 points. So what I want you to do is take your string, stick it with your thumb on the edge of the table at infinity, right? So we're going to guess. So we first guess. Okay, so I'm going to put my string here. If you want more colors, feel free to have the person next to you tape little strategic dots around as you figure it out. We're going to take our string. So let me find, I need a piece of string to show you guys. So I guess that, oh, this might be the center. Just because I'm special and I was maybe smart, I put it right here on the edge of the table, and I take my finger up to the first point. Because it's string, it tells me the radius is this long. I just see if I missed it. Oh, I missed it. Right? So now I move the string a little bit to account for that and try it again. Oh, missed that one. So I push up and move the center until I get it right. Oh, I'm not getting it right, so I try way over here. Oh, that's way off. So maybe it goes over here, right? Oh, that's closer. And I sort of keep track of where my thumb is. Whew. And I got it. I have the center. See, this is where it helps to have a friend, because now I can't draw it. But I at least know where the center is. So since I know the center now, this is the center of the circle. I then know that this distance from here is the same as this distance. So you see how we could write down equations to solve for this, right? Because we know exactly where the x value is. We're in the complex plane. So once you figure it out, now what I want you to do is use more masking tape and mark where the geodesic is going to on the real axis. So have your neighbor help you and mark the endpoints of the green geodesic once you've found, or the geodesic through the 2 points. You're getting close. Yeah, it helps to have a friend.
Do you want me to help you?
Remember, the important part is the center of the circle.
You can hold it, yeah. Okay, here. All right.
That's a smart way of doing it.
So I guess just shift that down. This will have to be down. And yeah.
Oh my God, you've broken the hyperbolic plane.
Thanks.
That's okay though.
I kind of missed.
It's a little space.
So it's like that. And then
Getting pretty close.
slide this over.
Another thing you can do.
Do I hold this point here, or do I?
Take some tape and mark where the geodesic hits the boundary. Right? So shot off a new geodesic to infinity. Right? What type of angle do you want to say there is at the boundary where you are standing of those 3 lines that you drew on the table or taped to the table?
Something non-negative.
Like what is the angle? What is the angle that these 2 rays are making with each other? With each other. Right? They're going into the line in the same way. Right? They're coming together. These are 2 parallel lines in hyperbolic space approaching the same point. Right? So we want to say that there's an angle between them, namely the angle 0. Okay? These are shooting off to the point infinity. Right? In the same way. So we want to say that they're hitting the point infinity with angle 0. And likewise here. So what we've just done from 2 points is built this ideal triangle where the 2 points lie on one side of the triangle. That the triangle we built, all angles are 0. And we did it. Look at all of them. Aren't they great? Woo! Yeah, well done. Well done. Okay. And now I want to inform you that it's not that hard, but there's an easier model. So let's get some string and come over to the circle. So we're going to do another. So just circle around so we can see the table. We're all standing at infinity now. right? Awesome. So I need 3 strings, right? Because I'm making a triangle. It's going to have area pi, by the way. Okay. Now, someone mark 2 points in, what should we do? What model? It's not up. I erased it. No, we should not do the conformal one. That's the hardest one. We should do the projective model, okay? Where straight lines are straight lines, right? Okay, so mark 2 points on the table. We should probably put some tape down and mark them, right?
Anywhere at all?
Yeah, it doesn't matter.
Stick one there.
Okay. And I'll put one right here. We need a pencil so we know we're being kosher. Okay, so we're doing the same thing that we did over in the other model, right? So I want to make the geodesic that connects the two. So someone help me. So we hold our line straight and we just go over the points like that. Oh. And we tape them to the boundary. Oh, could someone help? Okay. Now, this is where it gets a little more subtle, is what did we do over here? We shot the 2 rays to,
Infinity.
where's infinity? We're all at infinity, right? I told you we were all standing at infinity, but this one shot off to the infinity symbol in the upper half plane. Where's infinity here? Think about, so if we look at the picture of the upper half plane model, if we wrap the real axis around, we'll get to a point, right? Which was labeled? Yeah. So there happens to be a nice analytic map of the upper half plane to the disk that takes the real axis to the circle. So we're set. So we just need to choose where infinity is. See the choice involved? We have to decide which point is labeled infinity. It didn't matter in drawing this geodesic at all when I had 2 points inside the space. But now to choose to draw the same type of triangle we did over here, we actually have to label something infinity. So someone put a label on the boundary and label it symbol infinity. Sure. So we're going to label this infinity right there. Okay? Now we just need to shoot 2 rays from this infinity. We need to shoot a line to that infinity. So here, someone help. So I need to shoot a piece of tape. So in the projective model, you just put them together and tape it on the boundary. There we go. And now do it over here. There we go. So losing angles at the penalty for easily making triangles is often wanted, right? Now, let me draw for you the last model. It's a little harder, so let's see where we've all made some nice triangles. So we made a whole bunch of triangles, all whose angles are 0. All have area pi. In fact, so there's a thing, like I like action, right? I study groups acting on spaces. Okay? In particular, a special type of action is one that doesn't mess with distance. Okay? I haven't told you any of the distances associated to this crazy space. But we can talk about some actions at the end that will show us how we can move these shapes into the pictures we saw on the poster. Okay? So that's just a little, let's see if we can get there. Okay, so the next model that I want to draw for you is the hyperboloid model. Well, I guess I'll start with a little preamble. It's a little harder to define, but it's a little more concrete. We can actually do a lot of calculations on it. This is the closest to actually visualizing the curvature, but there's still distortion, so don't believe it's exactly the hyperbolic plane. There's slight distortion in this model. So the way we start is we start with the vector space R3. Okay? So this is where we live, R3. But there's no distance yet. There's no notion of line or just subspace. We only have subspace and affine space. That's all we got. Okay? So we pick a basis. I'm going to call the first one H. All right, this is a perfectly good basis element. I'm going to pick another one. Call it X. Okay? And what do you think the next one's going to be? Y. Okay? So here's the picture. Okay? X, Y, and H. Nice picture. Oh, but I need to tell you something else. I'm going to consider, so what am I going to look at? I'm going to look at vectors. So let's look at vectors in R3. And I'm going to write it in terms of the basis. So Vx, Vy, and Vh. Okay. Now, I'm going to build the hyperboloid now. So the hyperboloid is the V's such that if I look at Vx squared plus Vy squared minus Vh squared equaling minus 1. Okay? And in particular, I want the upper sheet, let's say. There's a choice because of the squares, right? The squares would allow me to actually send something with negative VHs. So I'm going to special condition of doing the upper sheet because I want to care about just the upper side. Okay? And that will be the upper sheet of the hyperboloid. So I'm going to also require that VH be positive. Okay? So you might, heavens, what does this look like? I just wrote down an equation, right? So let me do my best to draw it. Okay, note, I'm going to draw it a little bigger. This vector, H, is on the hyperboloid that I'm defining, right? There's some special vectors that are not on the hyperboloid, but that are special and help me draw it. Namely, the vectors when I plug into this equation that are 0. This is special. I'm using a color yellow for the light-like vectors. Okay? So we name all these different vectors. Well, maybe the physicist named all these different vectors. So note, if I move over the x direction 1 and up 1, I get a guy that, when I plug into this equation, is 0. So it's not on there. In fact, any scalar multiple, right, is not on there. All right, so it just shoots off. So likewise, if I reflect, it's going to be the same way, right? Right, there we go. So note, it builds a cone. Okay, so okay, So I haven't drawn anything except for one point on the light cone. Okay? If I were to go up 2 heights, so I went past the light cone, or past the hyperboloid at this spot, and I think of drawing things on the hyperboloid that satisfy this equation, you'll end up getting a circle that looks something like this. Right here. This is sort of the light cone at this, with vectors of VH at height 2. So the way geodesics look on the hyperboloid is it connects a point here, and then I'm just going to draw one like this, here and here. It connects it this way. Okay? And I picked this in a very special way so that it bends all the way down to the center H vector. Now what I'm going to do is I'm going to rotate it, flip it around. So note, I get pictures like this. So wait, this is solid. Solid again. And these are vectors that shoot off like this. And this sort of builds the hyperboloid. So we have right, something like that. So you see this sort of bowl that we're building? These are all the vectors that, when plugged into this equation, get me -1. And they shoot off, right? The coordinates get bigger and bigger. It's real values. Okay? So that's where we're sort of shooting off. These vectors, the yellow ones, are infinities, right? They're like the table. Now note, we can actually see this picture in here. Let's see. I'll draw it in red. This disk right here. So this disk is up height 1. So the vector H is at the center of this disk. Now, what happens to these blue lines? Well, see, this blue line is shooting off to an element over here in the perspective drawing, right? So if I were to project it down to this disk, there's a light-like vector, like this, that this blue vector right here goes towards, right? So I get this nice straight line, project it down. Okay, so there's this one. And I'm going to come across, let's see, which one did I do? I did this, which shoots across this way. So I drew it sort of poorly. We're going to erase this one. I'm going to erase this one so you'll see which one I'm projecting shortly. So I'm projecting this one. Okay. So there's another light-like vector that shoots out from the cone from behind. It goes out this way. And this blue guy right here is shooting off to that, right? And it projects down onto this. That's a straight line. Projective model, projecting the line down. Isn't that sweet? So how did I draw these lines? I didn't really tell you how to draw lines on the hyperboloid, right, like I did the other ones. It's a little more complicated, but it's not bad. So let me tell you what these blue lines are. I take a two-dimensional subspace of R3, right? It's a subspace, so it needs to have the origin. So it needs the origin, right? Which intersects I don't know how to spell. How do you spell intersects? S-E-C-T. The hyperboloid. The upper sheet. We usually stop just saying upper sheet because we're always talking about the upper sheet. Okay? So note, that's how I produced those blue lines. Is I thought of a subspace that connected all the that was close. Almost there. See, I need to make this line, right, when you draw this line on the blue plane, see, it sort of has to bend correctly. So let's pull this away so we can see which lines we're talking about. Right. See the plane now? See it? See how I've sort of cut into the hyperboloid? Sometimes it's hard to see the picture. But the blue plane cuts, it goes through the origin, it cuts this red line, the projected line that we did on the disk, and it traces out this blue line. Right? I should probably erase this one so we don't get distracted. And we get this nice line right there. That's how we build lines in the hyperboloid model. The Poincare model, the one that's the hardest to draw, is a similar type of, pulling down the vectors in the hyperboloid, but you actually have to look at the vector minus h. And you draw lines from minus h up to the hyperboloid, and you draw it on the disk in the xy plane. And that actually it's sort of hard to actually see, but it's a way to relate all three of these models together. Okay? And then you use the Poincare disk model to relate to the upper half-plane model. And this is, so the hyperboloid model is a great model to actually write down the explicit maps from one to the other. So you go to the hyperboloid model, and then you go to another model. You take the model, you go to the hyperboloid model, and then you go to another model. And that's usually how that's done. Okay? Sweet. So where's the triangle? Let's draw the triangle. Let's see if I can do this. This is not the easiest thing to do. So note, I have my blue plane. I'm going to think of drawing this triangle. So this is the triangle we have on the table, right? This is in the projective model. I'm going to unproject it. I'm going to pop it up. So maybe use green if we can see it. So I start with this guy. It comes down. Then back up all the way this way. Okay, so I connected here with the blue plane in here. So a little bit over is where the red line will connect with it. And it shoots over to something that shoots off to this light-like vector. So it shoots like this. And it comes down, shoots off. Now, I need to think of a plane that goes through the origin that is tilted to this red line here. So in perspective, this sort of cuts it a little bit beyond this. So it actually comes down something like this. And it's hard to see, but this is shooting off like this. I need to erase some of the blue. So we build our wonderful triangle that way. So this has crazy, it shoots off to infinity in this model. Really weird, like this. You guys see the triangle yet? This is the back side of the triangle, right here. Right? And it flips around and it gets me this. So isn't that a weird triangle? And remember, the hyperboloid is hiding some of the triangle. There we go. So maybe this is behind the hyperboloid. We'll strengthen the look of the hyperboloid now. So note, this comes down like this. So we sort of, you see how the triangle bends around? And note what, they're going off and approaching a light-like ray here, right? Here's the green. This edge of the triangle shoots off, and both are approaching that vector, like that. So again, we can see that the angle we're going to want to call 0 again. And that's how we do that. So this is the more complicated picture to draw, but say I wanted to do some stuff with a computer, right? It's just a vector space, right? Where this formula should look awfully familiar if you've had linear algebra, except for this minus sign, right? And this is how we will use this model to lift up another dimension, right? And we'll keep the -1 in front of the height. You might want to change it to t for time if you're a physicist. And then with one more dimension, if you have x, y, and z, and a t coordinate, and then you look at equations like this, you get space-time. So this is the precursors to how to lift up some geometry of the plane into more complicated scenarios that we want to model that we perceive might have some hyperbolic structure. Okay, nice. So there's the models. There's the 4 standard models. We've built a whole bunch of triangles with all 3 angles 0. And I think I'm out of time. But note, things are real easy to do. Like, think about what rotation is about a point in this model. It's pretty easy. Say I want to rotate by pi. Let's start with an easy one, right? That's just flipping around, right? So if I think about what's happening on the boundary, say I pick a point here, and I want to rotate by pi around my finger, then I know what my infinity point up here at the top is doing. I connect the geodesic between the point I'm rotating around by pi and I just draw the ray to the other side. And that's the line that's flipped if I were standing at this point. And then you could actually do it to all 3 points of the triangle, this ideal triangle, and see what rotation by pi does to this triangle. And we can also do it likewise over here, because rotation's just about which direction the ray is pointing, right? And what is fixed. So rotation by pi is very easy to see in all of these models. And we don't need to explicitly write down the coordinates. So we can see how triangles move around in this space when we rotate about fixed points by pi. We can see reflections really quickly. And that's basically how we build things that don't mess with distance, is we reflect and rotate stuff. All right, there we go. So this is hyperbolic geometry.
Thanks, speaker.